So we're in the Math 20 workbook on page 109, and today we're going to look at multiplying radicals. And so once again, it's just using your calculator to check whether or not the following statements are true or false. So thinking about it like an equation, so you can enter in on the left side, so root 2 times root 3, and see what the decimal approximation is for that, and then take a look at root 6 and the decimal approximation for that one. So let's take a look. So again, we can go second root 2, and then we just need to arrow over times root 3, and I can press equals from there. So approximately, and that's an irrational number, of course, so approximately 2.449 and so on. And then let's not hit clear, and we'll simply enter in the second root of 6, and you can see that it is exactly the same decimal approximation, which tells us that root 2 times root 3 is equal to root 6. So take a moment and go through the other examples as well. So this one is true. And just hit pause, and we'll come back and discuss what your conclusions are and what you think the rule might be. So for b, 2 root 5 times negative 4 root 3 is in fact true, that it is equal to negative 8 root 15. Root 2 times the cube root of 4 is not the cube root of 8. That is false. 2 times the cube root of 10 times 3 times the cube root of 7 is in fact 6 times the cube root of 70, so that is also true. And for E, 4 cube root 5 times 7 root 6 is not equal to 28 times the 6th root of 30. So hopefully your rule then was essentially that if we had, say, a root b multiplied by c root d, and we can maybe fix the index and we'll call it n as opposed to n and m, which implies that they might be different. If I have the nth root for both, it implies that the index is the same. So we are going to multiply the coefficients, so that's going to be a times c, and then we're going to keep the nth root of b times d. So multiply the coefficients, and the radicands, and the index stays. Okay, so again, you can see that they've got exactly the same thing written right below. So to multiply the radicals, the index must be the same. In each radical, we're going to multiply the numerical coefficients together and multiply the radicands, and then simplify into mixed radical form if possible. And so it is in fact typically easier to convert each radical into simplest mixed form before multiplying, mainly because it just keeps our numbers smaller. So it just kind of depends on the scenario, of course. So we'll take a look in a second. So if you have root 8 times root 8, so some of you might think of that as the square root of 64, which is in fact just 8. For root 5 times 3 root 6, so we'll multiply 4 times 3, and root 5 times root 6, so it's 12 root 30. 4 root x times 3 root y, so once again 4 times 3 is our 12, and we'll multiply the x times the y to make square root of xy. And then for this last one, so if you take a look at this, we have two ways about going through this. So the first way would be to simplify that root 8 and root 12. So these aren't huge numbers, so it's not going to be awful if we were to just go ahead and multiply, but let's take a look here. So we've got negative 2 times, and root 8 is the same as root 4 times root 2, times 5, and and root 12 is the same as root 4 times root 3. So we're looking at negative 2 times 2, root 2, times 5 times 2, root 3, or negative 4 root 2 times 10 root 3, and then again we multiply our coefficients, so negative 4 times 10 is negative 40, and root 2 times root 3 is root 6, and I should certainly double check that our radicand, and you should for all of them, to make sure that the radicand is simplified as much as possible. So alternatively with this guy, I'm just going to come over here, or the other thing that we could do is multiply right away. So negative 2 times 5 is negative 10, and root 8 times root 12, so if you know that offhand as a square root of 96, you can go ahead and do so. So you can see right there with the square root of 96, a lot of people have tough time identifying what perfect square factor goes into 96 because the number gets larger, and that's not even that big of a number, so you can imagine how much more difficult it could be. But then some of you might recognize, oh well, hey, 16 goes into 96, so I could have root 16 times 6, root 6, because 16 times 6 is 96, and so then that's looking at negative 10 times 4 times root 6, and of course negative 10 times 4 is negative 40 root 6, which is what we have over here. So it does, on the one hand, it does appear to be a shorter solution, but I will assure you that most times, especially when the numbers are larger, you're going to be much better off, especially if you don't have a calculator, to simplify those radicals first prior to multiplying. Okay, so let's take a look right here. So we've got root 5 times 2 root 10 minus root 5. So it says expand and simplify. So this goes back to multiplying polynomials. So it might be distributive property that comes into play as well. So a couple of things that I want you to think about actually even before we continue on. So I'm just going to come over to the side right here. So if I was to have root, let's say root 3 times root 3. Everybody hopefully at this point knows that that's equal to root 9, and that is of course just 3. If I was to take or square root of 4 times the square root of 4, that we could have two ways of going through that. We could say, oh well, root 4 times root 4 is root 16, which is simply 4, or of course because 4 is a perfect square, square root of 4 is just simply 2 times 2, which is also, of course, 4. If we looked at the square root of 5 times the square root of 5, then that is, of course, square root of 25, which is then just 5. Let's jump ahead a little bit. If I take the square root of 11 times the square root of 11, then that is the square root of 121, which is, of course, 11. So hopefully you're seeing the pattern then, that anytime that I'm multiplying the square root of a particular radicand, and if that number is the same, so if I was to take the square root of 37 times the square root of 37, I have no idea what 37 times 37 is. However, based on everything else that I'm seeing, the product actually should just be 37. Okay, so we can use that then right here. So if we've got root 5 times 2 root 10 minus root 5, so we're going to distribute that into both terms. So root 5 times 2 root 10 is 2 root 50, and then minus root 5 times root 5 is just going to be 5. If you feel more comfortable writing root 25 and then 5, that's fine as well. And then root 50 can, of course, be simplified to the square root of 25 times the square root of 2. So that's, whoops, minus 5. Don't want to forget that piece. So that's 2 times 5 root 2 minus 5, or 10 root 2 minus 5. And that's as far as we can get, because those are not like terms or like radicals. Okay, so let's take a look at part B then. So again, we're going to be distributing this through. And we can do a couple of things with this. So first off, I don't really want to multiply 5 times 45. That seems like it could be a little bit larger than I need it to be. So maybe I'll go ahead and simplify that one first. At the same time, if you take a look at root 5 times root 20, so we could do, a couple things with this. I could simplify root 20, or if you thought about it and you knew root 5 times root 20 is root 100, which is simply 10, that would be fine as well. It's just the idea that we've got lots of different ways to go through it, and you want to find what's going to work best for you. So let's just take a moment, and I'm just going to rewrite this with root 45 being simplified. So then that's 3 times root 9 root 5 minus 8 root 5 plus 3 root 20. And so, you know what, if you weren't comfortable with the root 5 times the root 20, and you want to make that root 4 root 5, that's totally fine as well. Okay, so let's just finish our little cleanup here. So root 9 is the same as 3, so we've got 3 times 3, which is 9 root 5, minus 8 root 5, and then plus 3 times root 4, or 3 times 2, which is 6 root 5. And look at that. I mean, even before, this is where you don't go into autopilot. So yeah, I could distribute, or wait a second, in brackets right here, these are all like terms that I'm adding and subtracting. So why not just combine all of those like terms before we multiply? So then we've got 2 root 5, 9 root 5 minus 8 root 5, it's just 1 root 5, plus 6 root 5, so that is 7 root 5. And look at how easily and how much simpler that got. Now we've got 2 times 7, which is 14, and then root 5 times root 5 is of course just 5, so 14 times 5, and there we have it. The answer is simply 70. Excellent. Okay, let's take a look at part C. And so we've got 2 times root 3 minus root 5, so that is simply going to be 2 root 3 minus 2 root 5, because of course this is our coefficient, and so you can only do radical times radical, or coefficient times coefficient, and so coefficients are of course 1 and negative 1 in this case. In this one, remember, you want to distribute negative root 2 into both terms. So we've got negative root 2 times root 6, which is negative root 12, and negative root 2 times positive root 10 is negative root 20. And so we've got a little bit of cleaning up to do with that root 12 and root 20 there. So 2 root 3 minus 2 root 5 minus, and this is root 4 times root 3, minus again root 4 times root 5, and so then this is 2 root 3 minus 2 root 5 minus 2 root 3 and minus 2 root 5. So combining our like terms, then we've got 2 root 3 minus 2 root 3, so that's just 0, and then negative 2 root 5 minus another 2 root 5, that's going to be negative 4 root 5, and there's our simplified answer for that one. Okay, taking a look at D, then we'll distribute this into both terms. We don't have like terms, root A minus 9 root B, so we just have to distribute. So negative 4 root A times root A is of course just A, so that's negative 4A, and then minus times minus is plus, and 4 times 9 is 36, and then we need to multiply those radicals. So root A times root B is root AB. And that is all we can do with that. Okay, if we take a look at class example number 3, then write and simplify an expression for the area of each shape. And so our first one is a rectangle, so of course area is simply equal to length times width, so area is equal to 7 minus root 6 multiplied by 4 plus root 6. And so this is where we've got a binomial times a binomial, which of course some of you think about as being FOIL, or so first outside, inside, last, or some of you might think about using going back to the box method as well, and either or would be just fine. So taking a look at that, so we've got first the 7 times the 4, which is of course 28. 7 times root 6 is going to be plus 7 root 6. And then let's go into that inside. So negative root 6 times 4, and then negative root 6 times positive root 6. So negative root 6 times 4 is negative 4 root 6. And then, I don't know why it does that. And then negative root 6 times positive root 6 is, of course, negative, and root 6 times root 6 is 6. So combining our like terms again, so 28 minus 6 is 22, and then 7 root 6 minus 4 root 6 is, of course, plus 3 root 6. So that is the area. If we wanted to be extra special, we'll say that it's squared units, so units squared. In B, we've got the 4 little ticks right here indicating that this is a square. So the area of a square, again, you can stick with length times width, or you can think of it as side squared, so either or. So if you were to write, if you wanted to write it as side squared, so 2 root 18 minus root 27, and that is squared. And of course, anytime we square a binomial, I would strongly recommend that you write that out, because we cannot simply square each term. That would be a big mistake, and quite a common mistake that people make. So again, you would need to look at doing FOIL or this your box method. So with this, again, there's a couple things that we can be doing. We can simplify root 18 and root 27, especially when we get into that outside and inside being multiplied together. I have no idea what 18 times 27 is. At the same time, I can quickly see root 18 times root 18 is just going to be 18. So let's just kind of go with that, and we'll fix it up as we go then. So when we do our first two terms multiplied together, so 2 root 18 times 2 root 18, so 2 times 2 is of course 4, and root 18 times root 18 is going to be 18. And then we've got our outside there, so 2 root 18 times root 7, minus negative root 27, sorry, so then that is minus 2. I'm just going to write root 18 times root 27 here, like that. And then again in the middle we've got the same thing, so negative root 27 times 2 root 18, so that's negative 2 root 18 times root 27, and then negative times negative is of course positive. Root 27 times root 27 is 27. So we can work on cleaning the root 18 times root 27 up as well. So 4 times 18, so remember to multiply by 4. An easy way is to double it and double it again. So 18 times 2 is 36, and double that again is going to give us 72. And then let's take a look right here. So I've got minus 2, and root 18 is going to be root 9 times root 2. And root 27 is again root 9 times root 3. And so then that is going to be the same again right here. So if you wanted to, what you could do as well is, because these ones essentially are both root 18 times 27, so we've actually got 2 of those. So rather than minus 2, I could do minus 4, just if that makes sense. And then plus 27. So let's take a look here. 72 plus 27 is 99, and let's let's take a look at what we've got going on here. So minus 4, and then root 9 times root 9 is of course just 9, so we've got 4 times 9, and root 2 times root 3 is root 6, so we've got 99 minus 36 root 6 then, and that is square units because we're looking at area. Excellent. Okay, so let's take a look at these. So multiplying conjugate binomials. And so when we take a look, we've got root 5 minus root 2 times root 5 plus root 2, and 2 root 7 plus 8, and 2 root 7 minus 8. And so my hope is that kind of reminds you of difference of squares, right? So difference of squares. So if you recall when we were doing polynomials, that was something that looked like x minus y times x plus y. So it appears almost exactly the same, except the sign in the middle is just switched. And when we multiplied those, we ended up with x squared minus y squared. So let's take a look at what happens when we've got conjugate binomials when it comes to radicals then. So root 5 minus root 2, so again, times root 5 plus root 2, so again we can do FOIL or we can do that box method. So root 5 times root 5 is simply 5, and then that outside is going to be plus root 10, the inside is minus root 10, and then the last is minus root 2 times root 2 is just minus 2. And so notice how, just as with x minus y times x plus y, those outside and inside ones cancel each other out because they are opposites. So we've simply got 5 minus 2, which is 3. So let's take a look at this other one right here then, the second example, 2 root 7 times 2 root 7. So 2 times 2 is 4. Root 7 times root 7 is going to be just 7. So we've got 4 times 7. And then our outside is minus 16 root 7. And our inside right here is going to be plus 16 root 7. And then positive 8 times negative 8 is minus 64. So we're looking at essentially 28. And then negative 16 root 7 plus 16 root 7. Again, those are their opposites, so they make 0. So we can leave that out. So it's 28 minus 64, which is simply then negative 36. So the best thing, hopefully, that you're noticing about the product, a couple of things happen. So the outside and inside essentially cancel each other out. The other thing is that the product is always an integer. So the product is always an integer. So that's going to come in really, really handy in a later lesson then. So, and you can see conjugate binomials, pairs of binomials in the form a root b plus c root d and a root b minus c root d. So they look identical to each other than the sign switching. And then the product of the binomials is always a rational number in the form of a squared b minus c squared d. So that looks way more complicated, but of course they're just multiplying a times a, which is our a squared, and then root b times root b is just b, and then c times c is c squared, and notice how the positive times negative gives us that negative right here. So it's that difference of squares. Okay, so 4 root 6 plus 3, so the conjugate then would be 4 root 6 minus 3. So just hit pause, write out the conjugates for the other two pairs for B and C, and then we'll go through and multiply those. Okay, so let's take a look. That first one we had 4 root 6 plus 3 times 4 root 6 minus 3. And so if you are ever unsure if, oh, is this the one where it's the conjugate? Is it not? You know what? Just always go through and continue to do FOIL, continue to do your box method so that you can confirm. If you are sure, then you know that if we've got a minus b times a plus b, then we know that we can simply square the first term, and then it's the difference of the square of the second term, so difference of squares. So 4 root 6 times 4 root 6 is then 4 times 4 is 16. Root 6 times root 6 is just going to be 6, so 16 times 6, and then it is minus 3 times 3 minus 9. So then we've got 96 minus 9, which is the same as 87. Then, so again, if you're not sure, go ahead and do that outside and inside as well, and hopefully soon you will start seeing that those actually are opposites and therefore they cancel each other out. So if we take a look at B, you can see I've got two versions written. So a lot of people right from the start, they just take negative 3 root 11 plus root 2, repeat those same two terms, negative 3 root 11, but instead of the plus, they're switching that sign to minus root 2. So that will totally work. Alternatively, what we could do is, just because a plus b is the same as b plus a, I could actually switch these around. So negative 3 root 11 plus root 2 is the same as root 2 minus 3 root 11, and therefore the conjugate for that is root 2 plus 3 root 11. So let's just go through then and then do multiply that out. So root 2 times root 2 is simply, whoops, sorry about that. So root 2 times root 2 is simply 2, and then minus 3 times 3 is 9. Root 11 times root 11 is 11, so 9 times 11, so why don't we just write that down then, which is 99, so 2 minus 99 is negative 97 then. So yet another integer. If you end up with a radical and you've got conjugate pairs, then you know that you have made an error. So in this case then 5 root x times 5 root x, so that is then 5 times 5 or 25. Root x times root x is just x, and then minus root y times root y is just y. So that of course is not an integer because we've got variables to begin with, but again you can notice that we have no radicals then. Okay, so thank you, and let me know if you have questions.